As I was walking across campus today, I saw all of the young people hurrying to their classes, and it just overwhelmed me. Just what a wonderful spirit you all have, and just the positivity that radiates from you. At the same time, just the number of overwhelming decisions that you have to make and the challenges that you face, and the fact that you have such a positive spirit and uplifting countenance, given all those challenges, just makes my old heart happy. You know, it's you that's going to save the world, and I appreciate you for doing that. Let's get started here. Again, we did very, very well on this exam. 80 is much higher than I expected on this exam. I always shoot for 75. Half of us got A's on that. We started this part of the class in chapter 10. Chapter 10 was where we talked about fluids and buoyancy, and we skipped chapter 9. And now we're going back to chapter 9. And the reason that I did it that way is because I would like to work some problems dealing with rotation underwater. Why wouldn't I? You know, and so I figured if we covered buoyancy first, then I could throw the water into these problems with rotation. Yes, I'm an evil man. We're going to start today with a demo that I call the Wheel of Death, and I need 2 volunteers to come up and help with the Wheel of Death. Thank you, Austin. Thank you, Josh. Come on up. Did you practice? Okay. Unfortunately, I think I miscommunicated to young Cutler. We need this pole here so that you don't get as hurt. I need each of you to hold on to one end of this pole and face each other. Well, I'll put this back together. Okay. Okay, now, oh, sorry. No. Okay, I need you to move over there away from the baby. Okay, let's just, yeah, let's do it over there. So I'm going to spin up this wheel, and here at BYU we have this motor to do that. In Montana we had to do it by hand. We're a poor school, but the church bought this for us. I can't hold it much longer, Captain. He's gonna blow. Okay. Now, I am going to hook this on here and on here. I need you gentlemen to hold this up high above your head. Okay. Okay. Now, Austin, I'm going to unhook that hook right there. You need to plan your life accordingly. Is that what you expected?
Oh, yeah.
About, yes, okay. Okay, we call that precession. And I do this to illustrate that there's some weirdness going on with rotation that we're going to have a little bit of difficulty explaining with the physics that we've learned so far. And so I'm going to, got it? Okay, let's give them a hand, folks. Just put that on the table anywhere. Now, I wish we had time for everyone to come up and hold this and try to change its direction. If I try to make it turn over there, instead, it goes in a direction 90 degrees to the way I'm pushing it. I'm pushing with my hand this way, and this end is going up. It just goes a completely direction 90 degrees to the direction you think it's going to go. Now, this has been used in television. Back when I was alive, there was a show called Candid Camera. And this was the early days of TV when everything was black and white, and we had 3 channels, if you were lucky. And this program would put people in an embarrassing or difficult situation, and then they had a hidden camera somewhere that they filmed it, and then everyone would laugh at them. And one of their more popular episodes was when they had a flywheel, a weighted wheel that was spinning inside of a suitcase. And then they would bring that suitcase in to the bellhop in a hotel. This was back when bellhops took your suitcase up to the room. And that bellhop would lift up the suitcase, and trying to take it to the room would turn, and the suitcase would just fly up like this, and we'd all laugh because it was so funny. But that's what we're going to try to explain in the next 2 lectures, is why that weirdness happens. Now, this is actually just the wheel of serious injury, and that's because a colleague of mine, when he was trying to put it back in the cradle there, he missed, and it took off across the table, and he grabbed it with his hand, and there was blood. So, but no one's actually died. Okay, let's start simple. I'm going to start with this wheel. Okay, there we go. Now, you see that I've got a red dot and a blue dot. And if I make it go once around, what can you tell me about the motion of the red dot and the blue dot? Which one went the greater distance? The blue one. Which one went the greater angle? They both went the same. And what was that angle that they went through? Tell your neighbor real quick.
He kind of zoomed up for a second.
60 mic notes.
Okay.
Keep doing the first time.
They went through 360 degrees. And that begs the question, why 360? Why not 240? Why not, 162? I believe it was 360 degrees because my parents taught me it was 360 degrees, and their parents taught them. And it turns out that 360 is a really, really useful number to use, because you can divide it by 6 and 9 and 4 and 3 and all sorts of different numbers. But I would like to suggest that that's not the way we were intended to talk about this angle. This is not the divine way to talk about this angle. A more natural measure of angle can be seen from this fact here, that if we take two circles, a little one and a big one, and we measure the radius of the two circles and also the circumference, the distance around, which we know to be 2 pi r, that if we divide the circumference by the radius in both of those circles, and indeed in every circle in the universe, we're going to get the same number, 2 pi, 6.28. Okay, and I'm going to suggest that's the universe's way of telling us, hey, that's how we talk about once around the circle, is 2 pi, 2 pi. Now, what we do when we measure an angle is we, let's say you had one of those compasses, not a Boy Scout or Girl Scout compass, but one of those pointy things that you're not supposed to run with. And I came out some distance r, and I use that compass to make an arc. Let's call that S initial there. Now, if I had gone out twice as far and made my arc, what we find is that it would be twice that original arc length, or I could have gone 3 times the radius from the point here, and that would be 3 times the arc length. You're seeing the picture, right? Okay, so it doesn't matter which of these I use. If I take the arc length and divide it by the distance out to where that arc length is, I get the same number. And I call that number the angle between this line and that line in radians. Now, on the first day of class, I asked you to check your calculator and make sure that it wasn't in radians, because that was going to be a disaster on the first exam. So when we talk about rotational problems, radians are the way to go, okay? And I'll show you later in the lecture just how much easier it is to deal with radians than degrees. Now, if I'm looking at 1 radian, how many degrees is that? Does anyone know? Brave soul, raise your hand. Anyone know?
90.
Okay, it's a little bit less than 60. It's 57. This is the way I remember it. If I go out 1 meter and make an arc length of 1 meter, that's going to give me an angle here of 1 radian. Now, I was a Boy Scout leader, a scout master for years and years and years. I also served for many years in a young single adult ward, and I would always joke to the young women that I'm the reason you have dates, okay? Because I didn't kill those young men in the scouts. I was going to, but I held back. Okay, they turned out great. Man, they were squirrely. Okay, so imagine that we are out on a camp out, and in Montana we camped through the winter, and we're trying to get out of a storm. So we find a piece of plywood, a great big sheet of plywood, and we use a stick to prop that up. Now the stick is bent. Now, if I were to push on that stick to straighten it out, the plywood would go to a bigger angle, would it not? And if I got that stick completely straight, this would be 1 meter by 1 meter by 1 meter. This is a triangle you've dealt with before, okay? And I would have 60 degrees here, and 60 degrees here, and 60 degrees up there, right? An equilateral triangle. Now, if with the stick straight, that's 60 degrees, if I then let that stick bend out again, the lean-to comes down a little bit. Well, 57 degrees. See if your neighbor followed that. And you can actually believe he was a scout leader.
My dad graduated.
Okay,
Neighbor on the bus. My grandpa.
now I could also have gone out 2 meters and found myself a 2-meter stick. Either way, okay? So that's 1 radian. So how many radians in 90 degrees? Let's use our clickers to answer that. Let me get you started. Okay, now you can click.
Less than 2 pi. No idea. Oh wait, not just less than 2 hours.
Okay.
Used to have.
Okay, last call. Let's get her done. Okay, good. The answer is B. Now, if that doesn't speak to your soul, let me help you. We can change units by multiplying by the number 1. Anytime you multiply something by the number 1, it stays the same. But there's lots of ways to write the number 1. For example, I know that 2 pi is once around a circle. I also know that 360 degrees is once around a circle. So this is just another way of writing 1. And now I can use this to convert degrees to radians, okay? If I move the 360 over here, I can see that what I have is 1/4 of the way around the circle. So if for Thanksgiving you have 2 pumpkin pies and you eat 1/4 of all the pie, you ate a half a pie. Does that make you hungry? Okay. So that's where we got the pie halves. Okay. Now, here's a sample problem that you might expect on an exam. We have a pulley of radius 4 meters, and we've attached this box to a string that's wrapped around the outside of that pulley. As the pulley turns through an angle of 43 degrees, what is the distance d that the box drops down? So with your clicker, and feel free to talk to your neighbor about this problem.
Yeah.
Went. Divided by 57. The word? An example that it's gonna be way easier. You knew not. And then we do the same thing with it in radians. And it'll be so easy.
Half the rate. Okay, I'll just.
Yeah, just, that's what you do.
No, it'd be fine.
Okay, if you haven't voted on an answer, do so now to get your clicker points. Okay.
That's overall.
Whoa. We're not sure. We're not sure. And that's exactly the result that I was expecting. And that's because what I'm trying to get across with this slide is that 43 degrees is very hard to work with. That's just messy. But if I had told you that that was a, well, first of all, can we all agree that in order for this box to drop a distance d, I have to let up an amount of string that is an arc length of d. That makes sense? Okay, anyone that's gone fishing knows that. Okay. Now, if I had told you that 43 degrees was the same as 0.75 or 3/4 of a radian, then this problem would have been easy and everyone in the class would have gotten it correct. But the 43 degrees is what threw you off. Let's solve it with the radians, okay? I know that the definition of the radian is just the arc length divided by the radius. Well, the arc length is the distance I'm looking for. That's d, okay? So if I solve for d by multiplying both sides by the radius and just plug in, well, I have 4 meters times 0.75 or 3/4 radians, and that's going to give me 3 meter radians, okay? So it drops a distance of 3 meter radians. Does that sound right? Does that feel right? A distance of 3 meter radians? No, we measure distance in meters. So if we don't like the radians, we just get rid of it. Is that? I've watched some of you do that. Okay, yeah. Oh, we don't need this here. Where's my eraser? In this case, it's legit because the radian is defined as an arc length divided by a radius, which is a length. So the units of radian is a meter divided by a meter, which cancels. The radian is just a placeholder to tell me I'm talking about an angle. It has no real units. So I can just disappear it when it's not needed. Okay, see if your neighbor followed that argument.
No, it doesn't have to.
Yeah. On the bottom.
It's a brief. My father left the PA. He spent like 20 years like as cardiologist.
Yeah.
Wait, too high.
Actually, it's like we create.
Yeah, 0.75 radians is 43 degrees. So if you have a button on your calculator that converts radians to degrees, that's what it would give you. Okay. So the question was asked, is 0.75 radians 43 degrees? Yes, that's how I got the 43 degrees in the first place, was by converting radians to degrees. Okay. Let's go on and talk about motion. Again, I've got a red piece of tape and a blue piece of tape here. If I spin that, what can I say about the motion of the red tape and the blue tape? Which one's moving faster? Yeah, in a linear sense, the way we were talking about motion at the beginning of the semester, this blue piece of tape has to go, you know, I'm not going to do nearly as good a job as the master teacher, Calvin's dad. Um, he explained things so well. Compare a point on the label with a point on the record's outer edge. Let's see. I missed this one here. Playing a record, you know what a record is. They're plastic, like a CD, but bigger. I'll show you something interesting. Compare a point on the label with a point on the record's outer edge. They both make a complete circle in the same amount of time, right? Yeah. But the point on the record's edge has to make a bigger circle in the same time, so it goes faster. See, 2 points on one disc move at 2 speeds, even though they both make the same revolutions per minute. There is not a way to explain that more clearly. I've tried. There is not a way to do it any better than that. And yet this is the result. Okay? This is the result. Now, I put that cartoon up there because I know that some of you, as we get closer to that next exam, are going to be feeling like Calvin, okay? And feeling like, oh, this is just all so confusing. It's not. You need to talk to me, you need to talk to Sam, you need to talk to one of the TAs in the help center and see just how much the same it is to where we've been. You've got to have that aha before you get to that next exam. Now, we call this rotational velocity or angular velocity omega, and we give it the Greek symbol omega as in alpha and omega. It's not a W, it's a Greek symbol omega. And what we see is that even though the blue piece of tape and the red tape have different linear velocities, the velocity we were talking about at the beginning of the semester, they both go through the same angle in the same amount of time. It takes both pieces of tape the same amount of time to go once around. And so the definition of angular velocity is just going to be the angle that it goes through divided by the number of seconds that it takes to go through. Now, remember, I've told you several times, when you have a definition that is a ratio, something divided by something else, if you want a gut feeling for what it means, set the basement equal to 1. In this case, 1 second. And that tells you what omega means. It's what angle do you rotate through in 1 second. In 1 second. Okay? Now, before we work this sample problem, let me just make one point. When we were talking about linear velocity, it was the linear displacement, delta x, divided by delta t. And I gave the example that if I took off running east and ran all the way around the world and came back to this very same point, my displacement would be 0. My average linear velocity would be 0 because half the time I was going east, half the time I was going west, it all canceled out. But with rotational motion, we don't cancel it out, okay? That's going to be 2 pi, 4 pi, 6 pi, 8 pi, 10 pi. I just keep on counting the angles as I go around. Now let's look at this sample problem. On a wristwatch that's analog, not digital, what is the angular velocity, magnitude, and direction of the second hand? Well, the magnitude is pretty easy, and this is a problem that's very similar to 2 of your homework problems for next Tuesday, okay? What I do is I say, well, that second hand goes around once every minute. Well, once around is 2 pi radians, and a minute is 60 seconds. So if I take 2 pi, which is 6 and change, and divide by 60 seconds, I get 0.1 radians per second. Okay? And that's the way you would find the magnitude. But what about the direction? Okay? What about the direction? Now, I would hope that with a clock, I could look and say, oh, you know what? That second hand is going clockwise. That's why we call it clockwise, okay? But let me just ask you, over there, clockwise or counterclockwise? Counterclockwise? Did they get it right? No. No, they're right. You're wrong. Oh, wait a minute. No, you're right. They're wrong. Clockwise versus counterclockwise depends on which side of the wheel you're on. Can we agree to that? And we found at the beginning of lecture today that with rotational problems, we often had this weird precession where you can't stay on the same side of the wheel. And so clockwise and counterclockwise isn't always going to work. Now, when we were dealing with linear motion, we used a vector. And that vector was a great big red arrow that went out our front windshield if we were going down the freeway. If we were in reverse, it was out the back windshield, okay? If I wanted to represent this motion with one single vector, one arrow, how would I point it? Talk to your neighbor. What would be the direction that I would point that arrow so that everyone would know how the wheel was turning? Circle.
Hi.
Okay. Here's where some of the weirdness comes in. If that wheel is turning, if I try to attach that arrow to, say, the rim, well, the arrow is going to change direction as the wheel turns. If I try to attach that arrow to the spokes, well, the direction of the arrow is going to change as the wheel turns. As this wheel turns, there's only one part of the wheel that's not changing direction. And that, my friends, is the axis, okay? And so even though it seems weird, we say that the omega vector, the angular velocity vector, points along that axis of rotation, okay? Now, it turns out that there are two ways to point along an axis. I can point out this way, or I can point that other way. And that turns out to be a feature, not a bug. Because once I've defined an axis of rotation, there's two ways that I can rotate it about that axis. I can rotate it this way, or I can rotate it that way. And so what I do is I assign one of those rotations to the red arrow and the other one to the blue arrow. Now, how do I know which goes with which? Well, it turns out that a committee met long before even I was born, and they came up with what is called the right-hand rule. And the right-hand rule means that when the wheel is rotating, you curl the fingers of your right hand in the direction of rotation, and your thumb is pointing along the axis in the direction of the omega vector. Okay? Now, if this were rotating the other way, I would curl my fingers of my right hand in the direction of rotation, and now my thumb is pointing out this way, behind the wheel. See if your neighbor learned a right-hand rule.
You do.
What is it? Kind of weird.
Clever than
The other side.
Okay. How many of you are left-handed? Raise your hand. No, your other hand. I'm kidding. I'm kidding. It seems like we are discriminating against left-handed people. And that happened again long before I was born. But in truth, we're discriminating against right-handed people. Because during that next exam, you're going to have to use right-hand rule over and over again. And that means that the left-handed people can use right-hand rule and still write their answers. Whereas the other people have to put their hand down and pick up their pencil. And okay.
Left-hand rule.
If you're left-handed, you have a statistically larger probability of becoming a scientist. You also have a larger statistical probability of going to prison. So choose now. Choose now. Okay, that's the right-hand rule. Now, we've talked about angular displacement. That's the angle through which it goes around. That's the theta. We've talked about angular velocity. That's the omega. That's the rate at which it's going. Let's talk about the last rotational kinematics topic, and that's alpha, which is angular acceleration. I'm going to start with a wheel that has an omega vector towards Sam, okay? And let's, seems like it's sagging a little bit. Okay, well, we'll deal with it. Okay, that omega vector is that way, and because it's spinning quickly, I'm going to draw it long. If I put my hand on the side to slow it down, it's still turning so that the omega vector is pointing towards Sam, but now it's turning more slowly. So I draw the arrow shorter. Now the question is, what change do I have to add that long vector to get that short vector? Well, my change in omega is going to have to be the other way. There's the plus sign right there, okay? The long vector plus this change gives me the later vector that's shorter. Now that change in omega that happens is going to give me my angular acceleration. Just like the change in linear velocity each second was what I call linear acceleration, the change in angular velocity each second is what I call angular acceleration. Check with your neighbor. No child left behind.
Just like, like the same ideas. Just.
Okay. Now, folks,
I felt like some.
I find year after year after year that a lot of people, once they learn the right-hand rule, want to use it for everything. Oh, omega's out of the page by right-hand rule. Alpha's into the page by right-hand rule. It's Tuesday by right-hand rule. The right-hand rule that I taught you is for omega, full stop, okay? There is no right-hand rule for alpha, for angular acceleration. There is no right-hand rule for alpha. For alpha, you have to do some thinking. If the wheel is spinning up, going faster and faster each second, then omega and alpha are in the same direction. Whether it's this way or that way doesn't matter. They're in the same direction. If the wheel is slowing down due to friction, then omega and alpha have to be in opposite directions. And again, it doesn't matter which one is which. Does this seem familiar? Have we been here before? Yeah, when you're going down the freeway, when V and A are in the same direction, you're speeding up. That's the gas pedal. When V and A are in opposite directions, you're slowing down. That's the brake pedal. It's all the same. It's all the same. Well, let's look at the similarity. You throw a ball straight up into the air with an initial velocity of 20 meters per second. How many seconds before it stops at the top? Shout it out. 2. Every second that goes by, we add 10 meters per second down. And if you started with 20, that takes 2 seconds to get all the way to 0. Okay? Well, if I had a wheel that is oriented like this, okay, and I had an omega that was coming out towards the class, and I had an alpha that was away from the class by slowing it down. Well, first of all, that wasn't always blocked off. We got a new version of PowerPoint, and it's Bill Gates did that. Okay. Now, I have a hard time drawing things in perspective, and so what I'm going to do instead is have that wheel flat on the screen like that. And that means my omega vector is going to have to come out of the page. And we represent that with a symbol like this that's supposed to look like the tip of that arrow. It's a point in a circle. And let's say that that initial omega or spin rate is 4 pi radians per second. How many times each second does that wheel go around? Twice, okay? Now the alpha vector, the acceleration vector, is into the page or into the screen. And we represent that with this symbol, an X representing the feathers of an arrow going away from you. And let's say that the magnitude of that is pi radians per second every second. So how many seconds is it going to take this wheel to stop turning? Hold up that many fingers. Yeah, 4. Thank you. We started with 4 pi each second, and every second that goes by, we subtract off pi radians per second. So in 4 seconds, this will stop. Yes.
Speeding it up instead of slowing it down, would the vector be going what?
Yes, if this were speeding up, both vectors would be coming out towards you, and I would use this symbol for both of them. Yeah, okay. Now, let's go back to the wheel of serious injury here. And what I am going to do, I'm going to try to do, let me just, oh no, it's not going to end well, is it? Okay. I was sucked into the wheel, got chopped up.
What?
You notice that this isn't slowing down very much in its spin rate, but its omega vector is changing. It's changing direction. Okay, so this should remind you of something from our linear study. And that is, let me put this away before someone gets hurt. By someone, I mean me. You remember that when we were going around a circle, Dave. It doesn't work with my dogs either. So when we were going around a circle with cruise control on, you remember that the velocity vector always stayed the same length. That's what cruise control means. But the direction of the velocity vector was changing. And we found in that second tutorial that that meant our acceleration vector had to be 90 degrees to our velocity vector as we went around the circle. Well, we've got the same thing going on here. If we had an alpha that was in the same direction as omega, the wheel would spin faster. If it was the opposite direction of omega, it would spin slower. That's not what's happening. And so the only thing that's left is perpendicular. And so as that omega vector changes its direction, my alpha vector has to be perpendicular to omega, just like in linear motion going around the circle. Talk to your neighbor again, do a buddy check.
How does the what you say? This is saying that
When it changes it.
it's just saying that it doesn't.
But the normal then.
Okay, now
But not like it there, yeah.
this is where I give you good news. You spent a lot of time learning how to do one-dimensional motion problems. And what we're going to find is that everything we learned there is going to be repeated now with rotational motion. Because of the definition of linear acceleration as a change in linear velocity with respect to time, and angular acceleration as a change in angular velocity with respect to time, we get exactly the same formulas, okay? It's just wherever we have a linear velocity, we replace it with an angular velocity. Wherever we have a linear acceleration, we change it with an angular acceleration, alpha. Time is time. And whenever we have a linear displacement down the road, we replace it with an angular displacement around the wheel. And we get 4 equations that are completely analogous to what we used before, the ones that were on page 23 of your textbook, okay? And we solved these rotational motion problems in exactly the same way. You remember the recipe. We made our list of the 5 variables. We had to find 3 of the variables from the problem statement. And then we looked at which one that was left we needed and which one we didn't care about. Well, let's use that technique to solve this problem. The drill bit of a variable speed electric drill has a constant angular acceleration of 2.5 radians per second each second. The initial angular speed of the bit is 5 radians per second. After 4 seconds, what is the bit's angular speed and what angle has the bit turned through? Well, let's follow the recipe. Remember, if you follow the recipe, you don't actually need to think deeply about the problem. You just go through the motions. In the olden days, I would make this list: delta X, A, V initial, V final, delta T. But with rotational problems, instead of delta X, I'm going to have delta theta. Sam, could you get rid of that wheel for me? Thank you. Instead of linear acceleration, I have angular acceleration. Instead of linear velocity, I have angular velocity, and time is time. Now I need to find 3 of these from the problem statement. I'm told the angular acceleration is 2.5 radians per second squared. It starts with an angular velocity of 5 radians per second, and the time is 4 seconds. Now in the first part, A, I want to find this final angular speed. That makes this delta theta the who cares. Well, if I don't care about the displacement, then I use the equation that doesn't have displacement in it. Omega final is equal to omega initial plus alpha delta t. If I go back, you see that all of these equations have delta theta in it, except for the first one. And so I'm going to use the first one here. This is going to be 5 radians per second. And then I'm going to add 2.5 radians per second, each second that goes by for 4 seconds. That's going to give me 5 radians per second plus 10 radians per second equals 15 radians per second. So now I can go and plug this in. And when I solve for part B, what angle has the bit turned through? Now this goes from who cares to being worth $10,000 in a houseboat, okay? And because I have 4 pieces of information, there's going to be several equations, indeed 3 equations, that will each give me the same correct answer, okay? And if I plug into one of those equations, let's do this one here. Delta theta is equal to 1/2 omega initial plus omega final times delta t. You recognize this is just the average angular velocity. So that's going to be 1/2 times 5 plus 15 times the time is 4. 5 plus 15 is 20. Half of that is 10. 10 times 4 is 40 radians. And that's going to be about 6 rotations and change. Okay. Questions on that problem? Let's look at this one here. A basketball player is balancing a spinning basketball on the tip of his finger. The angular velocity of the ball slows down from 18.5 radians to 14.1 radians, during which the angular displacement is 85.1 radians. Determine the time it takes for this to happen. Well, I go back to my list and I find 3 of the things. My initial omega is 18.5. My final is 14.1. And it goes through an angle of 85.1. That leaves 2 blanks. And I'm asked to find the time. And that means I don't care about alpha. Now, before I stop caring about alpha, what if I did care about alpha? Would I expect to get a positive or a negative answer for alpha? Tell your neighbor. Positive or negative? If this ball is spinning that way, the omega vector would be up towards the ceiling by right-hand rule for omega, okay? By calling that positive, I have set up a coordinate system where up towards the ceiling is my positive y direction. If this ball is slowing down as time goes on, that means my alpha vector is going to have to point towards the floor. And so I would expect to get a negative answer for alpha. But in this problem, I wasn't asked about alpha, I was asked about time. So I'm going to use the formula that doesn't have alpha, the same one we just used. So this is 85.1. This is 1/2 times 18.5 plus 14.1 delta t. So 85.1 is equal to, let's see, if I add these two together, I'm gonna get 32.6. Half of that is 16.3 times delta T, and 85.1 divided by 16.3. Quick, Sam, what is that? 5 point what? 5.3? Close? 4.2?
5.2.
I can't hear. I'm gonna use my calculator. That's not right. Anyway, it's some number that we don't care about. Okay, that's how you would solve the problem.
Like, we don't.
Okay, Sam cares. Okay, 5.22. Okay. We have just a couple of more key ideas that we need to handle so that you can do your homework. Suppose we are looking down on a merry-go-round, like we are Jonathan Livingston Seagull looking for a target. And on that merry-go-round, there's a little red-headed kid and a little blue-headed kid, okay? And we want to know which of those kids, the red-headed or the blue-headed kid, has the greatest centripetal acceleration. Centripetal acceleration. You remember centripetal means center seeking. The V squared over R that we talked about when something was going around in a circle. Well, that V squared over R, the V is the tangential or linear velocity, the velocity that's always tangent to the circle that they are going in. So with your clicker, which do you think has the bigger V squared over R, the red-headed kid or the blue-headed kid, or both the same? Now you can click.
Yeah, it's a circle.
Like if you're spinning around. No. Linear, then it's.
Okay, last call. Get your vote in. Last call.
Good at thinking about
Okay, we are all over the map on that. And that's okay, because this is new territory. To answer this question, we're going to need the help of the 5 Svensson brothers. This is Sven Svensson, his brother Sven, his other brother Sven, his other brother Sven. They're quintuplets, okay? And their skill is that they can figure skate in a straight line. Now, clearly this Sven is not as good a skater as this Sven. Okay, he just kind of does this. Now, it seems obvious that this Sven has to skate faster than this Sven. But how much faster? How much faster? Well, let's use our definition of the radian to answer that question. It turns out that if we look at this Sven right here, S is the arc length from when they started to when he got to that location there. The R is the distance away from his brother at the center of this circle. Now, the theta is the angle through which all of the Svens have rotated through, because they're moving in a line. Now, if I divide both sides by delta t, first of all, I multiplied by R, and then I divide by delta t, the S over delta t is the linear distance, the arc length that Sven travels, divided by the time. That's the tangential velocity, the linear velocity, okay? On the other hand, the angle divided by time, that's the angular velocity. Now, we can agree that all of the Svens have the exact same omega. Every point of a wheel has the same omega, if it's a rigid wheel. But they have different linear velocities depending on how far they are away from the axis. If he is twice as far away from the pivot, he has to skate twice as fast as his brother. That makes sense? Okay, now let's go back and look at the red-headed kid and the blue-headed kid. When we talk about the acceleration in terms of linear variables, it's hard. The V is going to be bigger for the blue-headed kid, but the R is also bigger for the blue-headed kid. Which wins? And so if we change that to the rotational variables with this equation, I just replace the tangential velocity for R omega. I have to square everything in the parentheses. I cancel one of the R's. The omega is the same for each and every kid on that playground, on the merry-go-round. Whoever is further from the center is going to need the bigger centripetal acceleration to stay on the ride. And that means they're going to have to hold on tighter out on the edge. And you've experienced that. When you're in the middle of this merry-go-round, it's easy to stay on. When you're out on the edge, you have to hold on for dear life. Now, there's just one more idea that will get you ready for homework. And this idea relates the linear motion of a car to the angular motion of the wheels. And it's really, really easy. We've been here before. If Jeff is walking relative to this boxcar at 5 meters per second to the right, and if the boxcar is moving relative to the ground at 30 meters per second to the right, Greg, standing next to the tracks, sees Jeff moving how fast? Shout it out. 35. We call that a Galilean transformation, okay? Now, what if Jeff is moving to the left at 5 meters per second relative to the boxcar, and the boxcar is moving relative to the ground at 5 meters per second to the right? When Greg looks at Jeff, how fast does he appear to be going? Shout it out. 0. Hold that thought, okay? If we take my old car, an old Chrysler Cordoba, and we lift it up on this jack, and then we get in the car's not moving, but I turn on the engine and I get the wheels turning, and it's a rear-wheel drive, it's an old car. First of all, what's wrong with that omega vector? Tell your neighbor why that's not only wrong, but sick and wrong. Sick and wrong.
Pointed on the axis. So
Okay. Remember, vectors can't bend. Vectors give one direction only, and so they can't be curved. The actual omega vector by right-hand rule would be into the screen, and I would draw that with an X in a circle. Now, if I were to take some blue ink and I would put a spot of blue ink on the top of that wheel, what we learned about from the Svensson brothers was that the linear velocity of that blue ink would be R omega to the right. If I put red ink on the bottom of that wheel, it would have a linear velocity that would be R omega to the left. Okay, that's just what we learned from the Svensson brothers. Now, if I were to lower that car slowly, listen carefully, I get screechy going on. And that's not what you get when you go down the road unless you're a 16-year-old male or the night rider. Hasselblad, whatever his name is. The Germans love that show. Anyway, we don't want that screeching going on. So we're going to raise that car back up. I'm going to get behind the car and I'm going to push. The lift is on wheels. I'm going to push the car to get it going at some velocity. And the question is, what velocity would I need the car to go so that when I lower it down, I don't get the screeching anymore? Remember this picture. Okay. So, what velocity? R omega. R omega. Because if that red piece of rubber that where I made the mark is moving this way, R omega relative to the car, and the car is moving R omega this way relative to the road, the bottom of the wheel and the road are not moving relative to each other. Now this gives us what we call the rolling condition. It should be called the rolling without slipping condition. And this condition relates the linear velocity of the car down the road with the angular velocity of the wheel. Now, we have 2 minutes left. This rolling condition also has some corollaries. Okay, if I know the angular displacement of the wheel and the radius of the wheel, I can also tell how far down the road it goes. If I know the angular velocity of the wheel and the radius of the wheel, I know how fast it's going down the road, what's on the speedometer. If I know the angular acceleration of the wheel and the radius of the wheel, I know how much the car is accelerating, speeding up or slowing down as it goes down the road. Folks, that's everything. That's rotational kinematics all together. Now, if you want a paper copy of this week's tutorial, pick one up on your way out the door. We've got some here and we've got some there.